October 17, 1944, Ledo, Assam, India. Captain James Mitchell of the 775th Engineer Petroleum Distribution Company stood at the edge of the jungle trace, staring at what should have been impossible. Behind him, trucks from the 330th Quartermaster Battalion had just delivered another convoy of aviation gasoline to the forward airstrip at Myitkyina, 400 miles into Japanese-held Burma. The trucks had arrived empty. Not carrying fuel, not burning fuel to deliver fuel, just empty. Mitchell pulled out his logbook and ran the calculations again. Each truck had consumed roughly 200 gallons of gasoline to make the round trip over the Ledo Road. Each truck had carried exactly 200 gallons to the airstrip. The mathematics were brutal. For every gallon delivered to the B-29 super fortresses preparing to bomb Japan from Chinese airfields, 5 gallons were burned just getting it there. Except these trucks hadn't burned anything. They'd been refueled directly from a 4-inch steel pipeline that now snaked alongside the entire length of the Ledo Road, a pipeline that climbed over 3,700-foot mountain passes, crossed monsoon-swollen rivers, and cut through terrain where Japanese snipers still operated. Mitchell had helped build sections of it himself, coupling pipe in waist-deep mud while mortar shells landed in the surrounding jungle. The strategic absurdity of the truck system had become inescapable by mid-1944. Operation Matterhorn, the B-29 strategic bombing campaign against the Japanese home islands, required massive quantities of aviation gasoline to be stockpiled at advanced bases in Kunming, China. The only land route into China was the Ledo Road, a mud and switchback nightmare carved through mountains that British railway surveyors had deemed too difficult for even a railroad. Trucks driving this road consumed more fuel than they delivered. The hump airlift C-46 and C-47 cargo aircraft flying over the eastern Himalayas could supplement but never replace ground transport. Aircraft losses on the hump route averaged 4 planes per day during monsoon season. Pilots called it flying the aluminum trail for the glittering wreckage marking the route through the mountains. The pipeline beside Mitchell's position represented a solution so audacious it bordered on engineering fantasy, pumped gasoline across 1,800 miles of mountain ranges through territories still contested by Japanese forces, using technology designed for short-distance distribution in flat, peaceful terrain. The concept violated every conventional wisdom about pipeline construction. Maximum practical distance for military pipelines was considered perhaps 50 miles. Elevation changes were supposed to be minimal. Terrain was supposed to be surveyed, graded, and secured before construction began. The India-China pipeline ignored all of it. It climbed from sea level at Calcutta to 9,200 feet in the Chinese mountains. It crossed the Patkai Range through Pongsa Pass at 3,727 feet, descended into the Hukong Valley, forded the Irrawaddy, Shweli, and Salween rivers, and scaled ridgelines where construction crews worked under fire from Japanese positions in the surrounding hills. It had arrived at Myitkyina days ahead of the Ledo Road itself. While road engineers were still blasting through the final mountain barriers to Kunming, pipeline crews had already laid steel to every forward position the Army could capture. What Mitchell was witnessing wasn't a support system for the Ledo Road. The pipeline had become the war's true supply artery. The Ledo Road now existed primarily to protect and service the invisible river of gasoline flowing through those 4-inch pipes. The relationship had inverted completely. This was an undeniable strategic reversal, proving the impossible possible. If you want to see how this discovery rewrote history, support us with a like. It helps us uncover more buried stories like this. Subscribe if you haven't already. Back to what this meant. The road served the pipeline, not the other way around. Mitchell watched another truck convoy depart from Myitkyina, each vehicle now carrying ammunition, medicine, and rations instead of fuel drums. The pipeline had freed the entire transportation network to do what it should have been doing all along, delivering everything except gasoline. The journey to this revelation had begun 22 months earlier, in the winter chaos of early 1943. On December 1, 1942, British General Archibald Wavell and American General Joseph Vinegar Joe Stilwell had agreed to make the Ledo Road construction an American operation under Stilwell's Northern Combat Area Command. After the Japanese seized Rangoon in March 1942 and cut the Burma Road, China had been isolated. President Chiang Kai-shek's nationalist forces were bleeding to death from lack of supplies. Soviet aid through Xinjiang was negligible. British aid through India was impossible without a road. The only supply route remaining was the Hump, cargo aircraft flying over the eastern Himalayas from airfields in Assam, India, to Kunming. But aircraft losses were catastrophic, and tonnage delivered was insufficient. China needed a land route immediately. Major General Lewis A. Pick, commanding the road construction effort, faced terrain that defied conventional engineering. The Ledo Road had to cross the Patkai Range through Pangsau Pass at 3,727 feet, descend into Burma's Hukong Valley, ford hundreds of rivers including the Irrawaddy and Salween, traverse over 1,000 miles of jungle where Japanese forces still operated, and connect to the old Burma Road near the Chinese border at Wanting. Stilwell's staff projected the completed road could deliver 65,000 tons of supplies monthly to China, far exceeding airlift capacity, which struggled to deliver 10,000 tons monthly even in good weather. Construction began on December 16, 1942, using the 45th Engineer Regiment General Service and the 823rd Engineer Aviation Battalion. The first convoy reached Xingbuyang, 71 miles from Ledo, on February 28, 1943. It took 73 days to build 71 miles of road through relatively accessible terrain. At that rate, reaching Kunming would require years. The fuel problem revealed itself during that first convoy. Engineers calculated fuel consumed versus fuel delivered, and the ratio approached 1-to-1. For every gallon that reached Xingbuyang, nearly 1 gallon had been burned getting it there. And Xingbuyang was just the beginning. Myitkyina lay 350 miles further, Bamo another 180 miles beyond that, and Kunming 500 miles past Bamo. The deeper the road pushed into Burma, the worse the mathematics became. Simple calculation showed that beyond approximately 400 miles, trucks would consume more fuel than they carried. The transportation system would become a closed loop consuming its own payload. Staff officers proposed increasing convoy sizes, improving road surfaces to reduce fuel consumption, using more efficient vehicles. None of it solved the fundamental problem. The distances were too great, the terrain was too difficult, the fuel requirements of Operation Matterhorn were too massive. General Pick recognized the crisis in those early calculations. On a morning in October 1943, he returned from inspecting a stockpile of 4-inch invasion pipeline sitting beside a railway siding in Ledo. Invasion pipeline, Victaulic coupled steel pipe designed for rapid deployment by combat engineers, had been shipped to the CBI theater for exactly this scenario, though no one had seriously contemplated using it across such distances. The standard application was connecting beachheads to inland depots, perhaps 20 to 50 miles maximum. Pick was contemplating using it for over 1,000 miles through mountains and jungle. He gave the order that changed everything. Start the pipeline. Private First Class Mitchell Williams of the 902nd General Service Battalion was unloading hay on that historic October morning when a sergeant told him to take 5 men and report to the pipe stockpile. Williams and his crew began stacking pipe, learning from Staff Sergeant Bill Watson and Technician 5th Grade Fred Cable how Victaulic couplings worked. The system was brilliantly simple. Each 20-foot section of 4-inch steel pipe had grooved ends. A rubber gasket fit into the groove. A 2-piece metal collar clamped over the gasket, creating a mechanical seal. No threading required, no welding required. 2 men could couple a section in minutes. The innovation had been developed in 1925 by Ernest Grove for municipal water systems. Traditional threaded pipe required each section to be rotated for connection, impossible in confined spaces or when working with long sections. Welded pipe was stronger but required skilled welders, power sources, and time. Victaulic couplings could be installed by minimally trained personnel in minutes, created flexible joints that tolerated ground movement and temperature changes, and could be disassembled and relocated if necessary. One day, Williams and his crew found themselves caught up with their usual work. Filled with initiative and the burning desire to push the war effort forward, Williams decided to start laying pipe. With no more ceremony than the command, "Let's go," they began coupling sections and laying line toward Burma. They had no formal training, no engineering surveys, no construction plans. They simply followed the road trace that bulldozers were cutting and coupled pipe as they went. Lieutenant Clark Nichol, a pipeline officer newly arrived from the States, discovered Williams' crew stringing pipe from a flat car and coupling it efficiently despite their complete lack of training. Each day, Williams would request just a few more men from his outfit, and soon he had an entire platoon working. Within weeks, the entire D Company of the 982nd General Service Battalion was laying pipe. By February 6, 1944, they had pushed the line to the 71-mile mark, the same distance it had taken road builders 73 days to achieve. In those early days, tools and supplies were non-existent. No wrenches were available, so ordnance companies fabricated them from salvaged 1-inch pipe. A few Indian axes and shovels were purchased locally. Cable for suspension crossings came from salvaged drag lines. When 2,000 feet of cable and 3/4-inch rope finally arrived, construction crews built trolleys to carry pipe over deep, impassable gorges into the jungle trace where it was coupled by hand. No surveyors laid out the course. 2 men walked ahead with Gurkha guides, cutting trace in accessible places, usually paralleling the road but taking every shortcut possible. The Stillwell Road at this time was barely a road, more an elongated construction site of mud, rock, and half-finished bridges. Chinese student drivers gained experience by driving regular army trucks up the unsurfaced road with supplies for pipeline engineers. Access roads either didn't exist or were impassable, forcing crews to dismantle pump stations and carry them into the jungle on their shoulders. The first refueling station opened at the 0-mile mark on the road. On February 4, 1944, the first truck fueled directly from the pipeline at Loglai at the 48-mile mark. The system worked. Gasoline flowed. Through the spring and summer of 1944, the pipeline became the shadow twin of the Ledo Road, always reaching forward positions before the road itself, always delivering fuel where trucks could barely operate. In late February 1944, the 699th, 706th, and 775th Engineer Petroleum Distribution Companies arrived in Ledo and took over construction. These were specially trained units whose entire purpose was pipeline construction and operation. None of their trucks, welders, or heavy equipment had yet reached the theater, so they borrowed what they could from road construction units. Small tools they'd brought proved inadequate for mountainous jungle terrain. From the beginning, these specialized engineers had to depend on ingenuity rather than equipment to maintain the rapid pace set for construction. Transportation remained the constant problem. Trucks depreciated catastrophically in the heavy hauling over mountain roads. A set of brakes lasted 1 month. Brake bands were almost unobtainable. Access roads were usually little more than jungle trails, but pipeline truck drivers became legendary along the Ledo Road for their ability to get loaded vehicles into any place their wheels could touch ground. Motor pool mechanics worked miracles keeping equipment operational. Vehicles were rarely deadlined for more than a few hours despite conditions that should have destroyed them. At Xinguiyang, aviation gasoline arrived via pipeline on May 19, 1944. The airstrip there was critical. It provided fighter cover for the American-trained Chinese divisions and Merrill's Marauders pushing south to take Myitkyina. Stockpiling sufficient fuel by truck would have required weeks and consumed most of the fuel delivered. The pipeline delivered it in days at zero transport cost. The pattern repeated at Tingkok Sakan. Road engineers were attempting the seemingly impossible job of bridging a 13-mile swamp that monsoon rains had converted into an inland sea. A one-way causeway operated, but traffic was so heavy that pipeline engineers couldn't monopolize its use. Given high priority, they worked mostly at night, taking pipe from trucks moving at slow speed along the bridge and walking it into position through waist-deep mud and water. Sections were coupled from boats and allowed to sink into the morass. When water receded in December, the pipeline lay on dry ground, a steel snake that had swum through the swamp. The job could have been done in a fraction of the time under normal conditions, but normal conditions didn't exist in Burma. Fuel reached Tingkok on June 10, 1944, relieving approximately 40% of truck shipments that had been battling the causeway bottleneck. By June 17, 100-octane aviation gasoline dispensed directly to fighter planes, bombers, and combat cargo planes at every airstrip in the forward area. The fuel simply appeared. Pilots didn't think about trucks or pipelines or logistics, they thought about missions. The pipeline made that possible. The fury of the campaign to drive Japanese forces from North Burma was constantly mounting, and petroleum demand increased proportionally. To meet the need, the 778th, 779th, and 780th Engineer Petroleum Distribution Companies were assigned to install a second line parallel to the first, a double pipeline system that could simultaneously deliver different grades of fuel to multiple forward positions. The line always went into operation as each section completed, meaning more trained engineers were continuously needed. In early August, the 776th Engineer Petroleum Distribution Company arrived in Assam and moved to Warrazup, where another airfield was under construction. Shortly thereafter, the 709th Company, which had made a splendid record at B-29 bases in India and had been seasoned by work on the 6-inch line from Calcutta to Tinsukia, was assigned to construct toward Warrazup from the opposite direction. The line entered the Mogung Valley, where jungle vegetation is reputedly the heaviest in all of northern Burma. The monsoon continued through a 45-day period during which pipeline engineers worked 12-hour days without dry clothes. Few had even a dry bed to sleep in. Keeping personal equipment usable became one of the biggest challenges. Heavy-duty army shoes had a life expectancy of 10 days in the mud and water. Jungle boots came apart in less than a week. Clothing mildewed in waterproofed bags. Men finally gave up trying to stay dry and worked shirtless in downpours, coupling pipe by feel in darkness lit by burning diesel in cut-down oil drums. The monsoon and jungle insects exacted a heavy toll. Malaria, dysentery, and typhus incapacitated large percentages of workers, but the work continued. Suppressive atabarine treatment and rigid malaria control became compulsory. With its administration, the malaria rate began declining until it became negligible. Vitamin deficiencies from lack of sunshine and Spartan diet imposed by absence of fresh meat and vegetables were partly remedied by daily vitamin tablet rations. Leeches became one of the biggest nuisances. When a man stopped for even a moment in the jungle, the creatures literally swarmed over him. Standing jokes circulated about running blood plasma through one of the lines to enable medics to replenish blood taken by the blood-sucking worms. Stories about snakes and wild animals became legend, but remarkably, there's no record of a pipeline engineer being harmed by either. Hunting offered about the only diversion, and many tigers and pythons were killed. Deer were abundant in North Burma, and parties regularly hunted venison for mess halls. The jungle was dangerous, but the work was more dangerous. Accidents, exhaustion, and disease killed more men than wildlife ever did. Indian pioneer troops proved invaluable throughout construction. These soldiers possessed high intelligence, and their ability to live and work in the jungle made them essential to American engineers. They primarily prepared pipeline trace and carried pipe and supplies into swampy jungles, but their aptness for the work made it possible for them to supplement skilled workers in actual construction. Without the pioneer troops, the pipeline would still have been built, but the cost in American health would have been tremendous. At Myitkyina, captured on August 3, 1944, after months of brutal fighting, the 775th Engineer Petroleum Distribution Company flew into the battered airstrip just 9 days later with 20 miles of pipe delivered by air. Fighting had officially ended, but expansion of air bases had to begin immediately even before the road was completed. Huge quantities of diesel fuel and aviation gasoline were needed at once, and a temporary pipeline offered the best solution. Before gasoline arrived at Warasup, engineers had begun constructing a temporary line via Kunming and Mogong, starting simultaneously at Myitkyina and Warasup. The only time the pipeline suffered enemy damage was at Warasup, when fragments from an exploding Japanese bomb punctured the line. Repairs were completed within hours. Only a combat trail existed between Warasup and Kunming, and it was impassable. Water stood 4 to 5 feet deep along parts of the proposed route. Tractors pulling pipe sleds bogged down. Only pontons and assault boats could move supplies into position. Some elephants were used, but they proved unsatisfactory due to the long trips and the inability of native handlers to understand the urgency. Pumps and pipe traveled by ponton rafts to Kunming, where 2 American trucks and some reclaimed Japanese vehicles were available. In some places, pipe was coupled into 600-foot sections on dry ground and floated into position. One 700-foot welded section crossed the Mogong River at its highest flood stage. To accomplish this submarine crossing, 5,000 feet of abandoned Japanese cable was stretched over the flood to a snatch block on a tree and back to the dry side, where a truck pulled the line across. When water receded, it was discovered that 70 feet of pipe would have been sufficient, but the job was done. Diesel fuel arrived at Myitkyina days ahead of schedule. Soon, 100-octane gasoline flowed into storage tanks at 200,000 gallons per day. While the temporary line was being built, other engineers had started the permanent double line to parallel the road cutoff to Myitkyina. Their work was completed and operational before the road was finished. By October 1944, 2 parallel 4-inch pipelines ran from Ledo to Myitkyina, a double system capable of delivering aviation gasoline, diesel, and motor gasoline simultaneously. Trucks now consumed pipeline fuel to deliver ammunition, food, and equipment. The fuel-to-deliver fuel paradox had been eliminated for the first 350 miles of the route, but Myitkyina was still 500 miles from Kunming. The most ambitious phase was just beginning. The turning point came when engineers recognized that conventional pipeline construction couldn't possibly reach China in time to matter. In November 1944, as Allied forces continued driving Japanese units south through Burma, planners confronted the timeline problem. The road to Kunming wouldn't open until early 1945 at the earliest. Operation Matterhorn required stockpiled fuel in China immediately. B-29s were already flying missions from Chinese bases, but every gallon of their fuel had to come over the hump at catastrophic cost in aircraft and crews. The mathematics of hump operations were almost as brutal as truck convoys. A C-46 or C-47 cargo aircraft flying the hump route from Assam to Kunming burned approximately 1,100 gallons of fuel per round trip. Each aircraft could carry perhaps 3,000 gallons of gasoline in drums. Delivery efficiency was roughly 2.7 gallons delivered per gallon burned, better than truck convoys over the Ledo Road, but still a catastrophic waste, and aircraft losses continued mounting. Between April and August 1944, the hump airlift lost 155 aircraft to weather, mechanical failure, and Japanese fighters. Each lost aircraft represented not just the crew killed, but also the cargo, usually fuel, burning in wreckage scattered across Himalayan mountainsides. The radical decision emerged from this calculation: build the pipeline simultaneously from both ends, starting construction in China while continuing to push east from Burma. This required flying entire pipeline companies over the hump with all their equipment, pumps, pipe, tools, vehicles, and starting work in territory where Japanese forces still operated in the surrounding mountains. It was insane. It was also the only option. In early November 1944, survey parties flew into Yunnan province and began working backward from Kunming toward the Burmese border. At times, work halted while Chinese expeditionary forces pushed Japanese units back. The surveys revealed an extraordinary opportunity. By following the straightest possible line across mountains rather than the Ledo Road's serpentine route, they could reduce pipeline length by 200 miles, saving 4,000 tons of pipe and 7 months of construction time. But it meant scaling 9,000-foot peaks and relying entirely on human carriers. The 797th, 780th, 1381st and 1382nd Engineer Petroleum Distribution Companies dismantled equipment and prepared for airlift. By mid-November, over 500 tons of personnel and equipment had crossed the hump. C-46 transports and CG-4 Waco gliders delivered pump engines to mountain positions. Gliders crash-landed on rough strips and were abandoned after unloading. In China, thousands of Chinese coolies worked alongside American engineers, carrying pump stations piece by piece up mountain trails. In one sector, pipe traveled 11 miles entirely on human shoulders. Each 20-foot section weighed 90 pounds. Teams of 4 men carried each section up trails where mules couldn't navigate. The pipe climbed to 9,200 feet, with most of the Chinese section operating above 7,000 feet. Engineers built suspension bridges spanning 5,000-foot gorges. Pressure differential from elevation drop became so extreme that only heavyweight pipe could contain it. Standard pipe would burst. Engineers calculated pressure at every point, adjusting specifications to handle forces exceeding anything in their training. Meanwhile, the Burma section continued east. At Bamo, captured in mid-December 1944, one detachment was unloading pipe from combat cargo planes on the first day the newly captured airport was operational. The Japanese stronghold had fallen, and 3 days later gasoline dispensed directly to trucks at the Bamo POL station. Engineers bypassed the town and continued toward China without pause. The line was always moving forward, never pausing, never waiting for perfect conditions. The philosophy was simple: couple pipe as fast as sections could be delivered, get fuel flowing immediately, worry about optimization later. On January 25, 1945, the first convoy over the completed Ledo Road, now officially named the Stilwell Road in honor of the general who'd conceived it, waited at Namkan for the final section to Wanting to be cleared of Japanese forces. Pipeline engineers waited at the same position, ready to connect the final link. The western section had reached the Shuili River, where pressure from tremendous elevation drop required heavyweight pipe through the valley. The double line had extended to Bamo and was serving planes, tanks, and trucks in the area. The line had been pushed east over the most rugged mountains in Burma and crossed the Shuili successfully. The Salween River had been cleared of Japanese forces, and a suspension bridge to carry pipe across the 5,000-foot gorge was nearly complete. Only a few miles remained to be connected before the line would reach its major China terminal. Supply in the China theater was never certain, but through improvisation and cooperation from China service forces, work never fell behind schedule. When the first gasoline arrived through the complete line at the first major Chinese-American base on April 9, 1945, 6 days had been cut from the original target date. Gasoline from Calcutta now flowed through 1,800 miles of steel pipe to arrive in Kunming. Every gallon that entered the system at Calcutta arrived in China. 0 transport losses. The fuel-to-deliver-fuel paradox had been eliminated completely. The design philosophy that made the India-China pipeline possible emerged from pragmatism confronting impossible requirements. The Victaulic coupling system was the foundation. Developed in 1925 by Ernest Grove, these grooved pipe ends with 2-piece collars and rubber gaskets created mechanical seals that 2 soldiers could install in minutes. The military had adopted it for amphibious operations, 4-inch steel pipe in 20-foot sections, each weighing 90 pounds. The system was designed for perhaps 20 to 50 miles. No one had proposed using it for 1,800 miles through mountain ranges. But the alternative was accepting that China couldn't be supplied by ground transport, that B-29 operations would be limited by airlift capacity, that the Pacific War would continue indefinitely. Petroleum pipelines require pumps every 50 to 100 miles to overcome friction losses. The Burma-China pipeline needed over 30 major pump stations, many accessible only by foot trail or glider delivery. Army engineers adapted commercial pump designs into man-portable modules, brute force engineering to make stationary equipment transportable. Each pump station supplied its own fuel from the pipeline itself. The elevation engineering was most complex. The pipeline overcame 11,500 feet of elevation gain and 23,500 feet of friction loss, from 300 feet in Assam to 9,200 feet in Chinese mountains. At Pangsau Pass, it climbed from 300 feet to 3,727 feet in just 61 miles, an average grade of 3.2%. Each pump station had to be precisely calibrated. Too much pressure would burst pipes, too little would stall flow. Engineers calculated pressure drops across hundreds of miles of varying elevation and temperature, accounting for viscosity changes, structural loads on suspension bridges, and where heavyweight pipe was necessary. Every textbook said it was impossible, every expert predicted catastrophic failure, but the alternative was accepting defeat before the battle was fought. The consequences of the pipeline's completion transformed this strategic calculus of the entire China-Burma-India theater and directly enabled operations that would have been impossible otherwise. At Kunming and surrounding air bases, B-29 superfortresses of the 20th Bomber Command now filled their tanks with gasoline that had traveled from Calcutta refineries without burning a single drop in transport. The 58th Bombardment Wing launched maximum-effort raids against Japanese steel production facilities in Anshan, Manchuria, on June 15, 1944, the first strike against the Japanese home island since the Doolittle Raid. Each B-29 mission required approximately 7,000 gallons of 100-octane aviation gasoline per aircraft. A typical maximum effort raid involved 50 to 100 bombers. A single mission consumed 350,000 to 700,000 gallons. Without the pipeline, these missions would have been impossible. The hump airlift could never have delivered sufficient fuel while simultaneously supplying other materiel needs. Calculations showed that sustaining B-29 operations from China using only airlift would have required dedicating the entire transport fleet solely to fuel delivery, with nothing left for ammunition, spare parts, food, or any other supplies. The pipeline made it possible. By May 1945, the system was delivering over 70,000 tons of petroleum products monthly to forward bases, enough to sustain continuous bomber operations, fighter sweeps, and ground force mechanization simultaneously. At forward airfields along the Burma Road, P-51 Mustang fighters and P-47 Thunderbolt fighter bombers operated with unlimited fuel availability. Close air support missions that previously required careful fuel rationing now launched at any hour. The 14th Air Force, operating from bases supplied by the pipeline, flew continuous interdiction missions against Japanese supply lines in southern China and northern Burma. Between April and August 1945, these aircraft destroyed hundreds of trucks, bridges, and ammunition dumps that would otherwise have sustained Japanese resistance. The Japanese army in China began to starve, not from lack of food, but from lack of mobility caused by American air superiority enabled by unlimited fuel. At ground depots throughout Yunnan province, mechanized units fueled their vehicles without the logistics nightmare of convoy protection. Chinese divisions equipped with American trucks and armored vehicles through Lend-Lease could now operate freely across the province, knowing fuel would always be available. The 30 Chinese divisions equipped and trained in India during 1944-1945 stopped the 11-division Japanese Ichi-Go offensive in East China, largely because they possessed mobility and firepower previously impossible when fuel had to be airlifted in limited quantities. The human cost of building the pipeline was tallied in increments of exhaustion and disease. Over 2 million total man-days of labor, split evenly between American soldiers and Indian, Chinese, and local workers, went into construction. Men carried 90-pound pipe sections up mountain trails for hours. They coupled sections in monsoon downpours. They operated in temperatures exceeding 100 degrees Fahrenheit in Burma's lowlands and below freezing at high elevations in China. Malaria, dysentery, and vitamin deficiencies rotated through companies. Engineers joked grimly about running blood plasma through a third pipeline to replace what leeches extracted daily. Some men disappeared into the jungle, never found. Others died in base hospitals from infections that penicillin might have cured. The pipeline was built on the backs of men who expected little and received less recognition than they deserved. Yet the pipeline never stopped operating once sections became functional. Fuel flowed continuously from the first delivery in February 1944 through the end of the war and beyond. Pump stations manned by rotating crews worked 24-hour schedules. Repair teams patrolled the line constantly, fixing leaks caused by ground movement, replacing sections damaged by falling trees or landslides, and clearing monsoon debris that could block flow. The system that shouldn't have been possible became the reliable baseline of Allied operations in China. Somewhere in the mountains between Burma and China, a pump station operator checked pressure gauges at 0300 hours during a monsoon downpour, making minor adjustments to keep fuel flowing. He didn't know which B-29 crews his work would keep alive tomorrow. He didn't know which Chinese divisions his fuel would mobilize next week. He knew only that his gauges had to stay in the green, and the diesel engine powering his pump had to keep running. That anonymous competence, multiplied across hundreds of men at dozens of stations across 1,800 miles, was how wars were actually won. The numbers tell their own story. Over 1,800 miles of pipeline from Calcutta to Kunming, 2 parallel 4-inch lines from Ledo to Myitkyina, extending through Burma to China. Supporting feeder systems included a 750-mile 6-inch line from Calcutta to Tinsukia. Over 50,000 tons of pipe, more than 500,000 individual joints laid across 3 countries. American soldiers worked over 1 million man-day on construction. Indian pioneer troops, Chinese workers, and local laborers contributed another 1 million man-days. Over 30 major pump stations were built, spanning elevations from 300 feet in Assam to 9,200 feet in the Chinese mountains, overcoming 11,500 feet of elevation pressure and 23,500 feet of friction loss. At peak capacity, the system delivered 70,000 tons monthly to forward bases. From project start to VJ day, over 150 million gallons of petroleum flowed through the ABC pipeline. Total petroleum products delivered exceeded 528,000 short tons. This capacity replaced 14,000 monthly transport aircraft sorties. The efficiency comparison was stark. Ledo Road trucks in worst sections, 5 gallons burned to deliver 1 gallon. Hump airlift, 1 gallon burned to deliver 2.7 gallons. Pipeline, 0 gallons burned. Every drop that entered at Calcutta arrived in China. On the morning of April 10, 1945, Captain James Mitchell stood at the Kunming terminal and watched Chinese ground crews fuel a B-29 Superfortress directly from a pipeline tap. The bomber's tanks held 7,000 gallons, fuel that had originated in Calcutta refineries 7 days earlier, traveled 1,800 miles through mountains and jungles, passed through over 30 pump stations, climbed 9,200 feet and descended to 2,600 feet, crossed 3 major rivers and hundreds of minor streams, and arrived without a single gallon wasted on transport. The aircraft's mission that night would target Japanese oil refineries in Palembang, Sumatra, a strategic strike designed to cripple the enemy's own fuel supply network. The irony wasn't lost on Mitchell or anyone else familiar with petroleum logistics. The entire Pacific War had fundamentally become a contest of petroleum supply chains. Japan had invaded the Dutch East Indies specifically to secure oil fields. Japan had attacked Pearl Harbor to prevent American interference with those oil supplies. Japan's entire strategic position in 1945 depended on maintaining fuel deliveries to forces scattered across the Pacific and Asian mainland. America had responded by building a pipeline over the Himalayas. Victory would belong to whichever side could sustain the flow of petroleum to its combat forces. By April 1945, that contest had already been decided. Japan's tanker fleet was being decimated by submarine warfare. Refineries were being destroyed by bombing. Supply lines were interdicted by air attacks enabled by unlimited fuel availability. The India-China pipeline represented more than engineering achievement. It represented the transformation of industrial capacity into battlefield dominance. The principles established by the India-China pipeline created foundational concepts for military logistics worldwide. Distributed construction networks, modular equipment design, rapid deployment protocols, and human-portable engineering solutions became standard doctrine. When the Korean War erupted in 1950, Army engineers built pipeline networks using lessons learned directly from Burma. The same Victaulic couplings, the same modular pump stations, the same rapid deployment philosophy. Engineers who'd built the India-China pipeline trained the next generation. NATO's Cold War fuel distribution planning studied the CBI theater case files extensively. The Central Europe pipeline system incorporated design principles validated between Ledo and Kunming. Modern military doctrine still relies on concepts proven in Burma: forward-deployed pump stations, flexible coupling systems, self-sustaining fuel supply, and the recognition that logistics often matter more than firepower. Every pipeline-supplied forward operating base in Iraq and Afghanistan descended from decisions made by General Pick in October 1943. The India-China pipeline taught a fundamental truth about modern warfare that remains valid today. Victory flows through the supply line, not necessarily through the weapon system. The weapon that wins isn't always the one that inflicts the most damage, it's the one that can be sustained in operation despite every obstacle enemy action and terrain can create. The B-29 superfortresses that burned Japan's cities in 1945 were formidable aircraft representing cutting-edge aviation technology. But they were useless without the unglamorous steel artery that delivered their fuel across the roof of the world. By August 1945, when atomic bombs ended the Pacific War, the pipeline had become so routine that few thought about it. Fuel simply flowed. The system that had seemed impossible 22 months earlier now defined normal. Pilots assumed fuel would be available. Ground commanders assumed mechanized forces could operate freely. All of those assumptions rested on 1,800 miles of 4-inch steel pipe that shouldn't have existed. After the war, the Stillwell Road gradually disappeared back into jungle. Bridges collapsed. Vegetation reclaimed the trace. By 1950, most of the road had become impassable, but sections of the pipeline remained operational into the 1950s, still delivering fuel across mountains where roads no longer existed. Chinese forces continued using the system. Some pump stations continued operating years after the war ended. The pipeline outlasted the road it was built to serve, a fitting legacy for the invisible lifeline that fueled the war's end. The road was visible, dramatic, celebrated. The pipeline was invisible, unglamorous, forgotten. But when history judges which mattered more, the answer is clear. The fuel reached China not because the road existed, but because the pipeline worked.